are still working on, and today we're going to finish off variable separable. So it's kind of where we are. So let's get straight into a question. Get my pen going. Okay, that guy there is a differential equation, obviously. It's got dy by dx in it, and it's first order. But it's not really written the way it needs to be. Great. To be variable separable, don't we need to have dy by dx on its own in a fraction? So the first thing we're going to do is get it into that kind of desired form, which is this guy. And I've deliberately chosen this question to be awkward. We have a fraction, but isn't everybody in the wrong place? Because when you do variable separable, doesn't all the x's have to be in the top and all the y's have to be in the bottom, right? The numerator, denominator thing. And they're not. And so we have to do some surgery to this thing. We have to fix it. Okay, if you take the y cubed and it ends up on the denominator at the bottom, what does it change into?
Y to the -3, and you do the same with the denominator and just raise it to the -1 power.
We all happy about that? Now, I'm going to do a little bit of different take on the top one. I quite like y to the -3 because I can use the power rule to integrate that. But you know x squared plus 1 to the power of -1, if you left it like that, you'd have problems trying to integrate it because it's really not written in a way that is suitable for integration. This fella here is the same thing as that guy, agreed? Below bracket random. Now, can you see the advantage of writing that is going to come later when we do the crossover integration? So we do the crossover. Then this fella is going to equal that fella. Now, do you notice how that is easier to integrate? We know, or we should hopefully know, what the integral of that is. If I'd left that as x squared plus 1 to -1, can you see you might start going weird places like u subs that don't work, or integration by parts, or you try one of the other techniques because it just doesn't look like that. But the minute you see it, you say, ah, yeah, I know this guy. This guy has an antiderivative of an inverse tan, of course, plus a c. And this guy is a power rule. So I'm going to add 1 to the power and divide by the new power. And we have that. And pause for a second, someone's just coming in. Now, don't we have a kind of style point rule that says, if you can, you should try and rewrite the solution in the form of y equals. And since there's only one y here, that means that this should be doable, right? We should be able to make this. So we're going to try and turn this thing eventually into y equals. But it's a good idea not to do too much in one go. So what might you start doing here? What could you do to both sides to get it closer?
Multiply by negative.
-4.
4 or 2? Which do you like?
2, sorry. I was doing it on my board and I wrote it down wrong.
Okay. So -2 gives you that. And we're going to stick to my rules. What will -2 times c get us?
C.
You'll get us c. Some of you have been doing the homework. My other class have been doing this, and I think the major issue tends to happen when it doesn't have a boundary condition. You know, when it says, you know, y of 0 equals 2. When that happens, it doesn't matter what you call it, it works. I think it's more likely when it's a general solution. Now, this fella here is better. I'm going to look at this fella and I'm going to think of him is that guy. Now, the reason I want to turn that guy into that guy is I've still got the goal of wanting y on its own, and I think this is going to help me. Now, a little algebra trick here. 1 over y squared is this guy. What will y squared be then?
Put everything under 1.
Yeah. And in this case, oops, y then is the square root of both sides. So technically, it could be plus or negative. Now we are finished as far as the general solution goes. So that's the general solution. But let's assume that this question, I'll bring this back in a minute, you were told that y of 0 was 1. Y of 0 was 1. Well, that is basically saying when x is 0, y is 1. And we call this piece of information a boundary or an initial condition. And it has one job. Isn't this piece of information going to allow us to find out what number c is? So I'm now going to focus on kind of the second half of this question. Right now, our general solution looks like this. If I can plug x equals 0 and y equals 1, I should be able to find out what c is. So let's go for the first thing. Since y of 0 is 1, does it not make y positive 1? And since it's positive 1, won't we only be able to use the positive square root guy? So I already know, without doing too much work, that it's the positive square root that's going to work. If this had said y of 0 equals negative 1, then I'd be using the negative square root. Right? So we get that for free. Now it's 1 over negative 2 inverse tan of x, I'd say. And now I'm going to replace the x with 0 and the y with 1. And I'm putting in probably more lines than you might do in your homework, but it looks something like that. Okay. The tangent, oops. The inverse tangent of 0 is 0. So that whole thing is 0. So what I've got is this. It's Katsumi coming in. So our goal here has been the same goal from the start, isn't it? To find out what number c is. So I've got an equation, and you're never sure what you're going to get in these questions. You've got to just deal with it. I want to eventually get c. So I'm going to use, as long as you do it to both sides, it's okay rule. So what should I do to both sides?
Square it.
And 1 squared is still 1. So that didn't do much. And I think I know what c is. You agree? Which means we now have our solution. There we go. And that guy is called a particular solution to that differential equation. Any questions about that? Are we good? Time to move on then. Okay, so we're going to solve this differential equation with this boundary condition. I get a problem. It's the usual. I need a fraction. Don't I need to get it into the standard form for variable separable? I need this to be a fraction. I need x's on the top. I need y's on the bottom. I think the x's are pretty straightforward, right? The problem is what's going to go on the bottom. Would you agree the square root of y is not very nice form for what I need to do? So what would I rewrite the square root of y was, even if I only do it in my head?
Y to the power of negative 1/2.
Okay, so y to half and it comes downstairs is y to negative half. Now that does two things. First, doesn't it make this bottom a lot more obvious? I don't think I'd want to call it the square root of y brackets to the power of negative 1. I mean, that would, I'm not even sure what that would look like, right? So that's helpful. And the second thing is when we do the next stage, that's actually going to be quite helpful to integrate. It's going to be in a nice format. So when we do the crossover, we get that. Well, power rule, add 1 to the power, divide by the new power. Power rule, add C. So far, so good. Would you agree that this is a candidate for y equals? So let's keep going. What could I do to both sides to get it closer to what I need?
Divide by 2.
Okay, so I'm going to take this, the y to the half and rewrite it as the square root of y. And I'm going to divide everybody by 2. And we're going to stick to my rule that C is still C. Actually, it's not just my rule. Lots of people do it. There's a 50-50 chance that you could guess this, but hopefully you're not going to guess it. What do I need to do to both sides to get y?
Square.
Root.
Agreed. And that would be the end of the question if they wanted you just to find the general solution to the differential equation, if you wanted to. But since you've been told this boundary condition, won't we find C to complete the question? So what do I know? I know that when x is 1, y is 4. So I know that guy's 4 when x is 1. So far, so good. Right, so we are going to take the square root. Now, technically, there are two possibilities here, aren't there? What happens if you take the square root of 4? You do get 2, but isn't there a second possibility? And that would simply just be negative 2. can we make the assumption that that it's positive? And I'm just saying it's positive because I want one answer. And if you subtract that from both sides, you're left with 5/4. And then you put that package together and you've got the answer. So what would the answer look like? It would look like 3/4 x squared plus 5/4 squared. Now, if you wanted to know,
I've got a question.
yes,
If in the initial condition, whatever the y value ends up equaling is positive, can we just always assume that it's a positive answer?
if technically you shouldn't, but if it's a square root, yes. So if it's a square root situation like the first question, it's totally okay to make that assumption. But in this case, I could have actually used a negative number. I would have got a valid value of c and it would have worked. So if they're going to give you a general, a particular solution problem like this, you need to be told in some way that it's positive. So I guess the only way that that would really work is if the question went and said that to you.
Thank you.
Okay, now, oh, is that the, are we good with that one? Right, because I'm going to be a real sneaky guy here. I'm going to give you a really ugly one. This is like question 11 in your homework. Okay. This is not very helpful, right? The form that this equation has been written in, this differential equation, is not helpful for the process I need. Is there anything you can think about changing this into? Another way of writing this?
Rewrite them separately.
That would be a good start. You know, we have to separate them. It's in the name, variable separable. It kind of makes sense that you should try and separate them, right? Now, would you agree that square roots are not very helpful in any of the questions we've done? So I'm going to replace them by half, oops, by half powers. And now we should be able to, with a little bit of extra work, convert that into a fraction where t's go on the top, right, and p's go on the bottom. Well, I kind of like those two guys. And that p to the half is going to go on the bottom, isn't it? The denominator. And what does he become?
P to the negative half.
Now, I've been saying this a lot, but it's actually something that you've done a way back when you did indices. Can you remember there was a property that went and said, there's an example of it, that 1 over a negative power was the same thing as a positive power? You remember that from, oh God, what was that, math 99, 94? Way back in the day. So
High
I'm
school.
using, say it again?
High school.
Or high school or someplace. It's one of those pieces of math that you think you're never going to use again. But haven't we found in calc that nothing goes, that's a double negative. Everything gets used again sometime, right? You might think, oh, I'm never going to use the quadratic formula again. And then there's just one question that you need to know it to move on, right? Or I'll never need to worry about 1 over a negative power being a positive or the reverse of that. And there's always going to be some question that appears. So anything you've done in your high school or at college, anything you've done in your math class algebraically, it's probably going to pop up now and again, no matter how advanced the math gets. Now, this guy is ready to go. And because I turned them into fractional powers, isn't that going to make the process of finding the integrals a little bit easier? So add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power. And we have now found, well, maybe not yet, I'm jumping ahead. We will, in a few moments from now, have found the general solution. There's only one variable here, which means it's a good candidate for converting into P equals.
Divide by 2, then square it.
Okay, so if you divide it by 2, you get that. And if you square that, you get that. And that would count as my general solution to this particular differential equation. Are we good? Right. There is a kind of flow to this, isn't there? There's probably going to be some algebra at the beginning so that you can get it into this form. The crossover is pretty straightforward, some integration, and then maybe some algebra at the end to get a P equals or whatever the variable happens to be. So far, so good. Right, let's use this fella now, this boundary condition, to get C. So I know that P is 4/3 T to that plus C being squared. And since P of 1 equals 8, you are telling me that when T is 1, P is 8. So that gets me 8. 1 to the power of 3 is still 1. So 4/3 times 1 is 4/3. And we got that. And yet again, every equation's a little bit different. We have to solve for C. What could I do to both sides?
Square root.
We'll assume it's positive, which it is. Now I want the exact value. And if I subtract 4/3 from both sides, I guess I do know what C is. But not only do we want an exact value, there's a kind of little underlying rule below that. Don't we want it to be as pretty as possible? Is there something that you could do with the square root of 8 that might look a little bit nicer, a little bit simpler?
Pull out the square root of 4.
So you end up with 2√2 take away 4/3 C, which means that we're using something from, I believe it's 99, which was how to simplify radicals. So there's another little piece of information that you thought I'll never need to worry about again, popping its little head up, right? The square root of 8 can be reduced to 2√2. Everything that you do, you should always have a kind of second look at it. Could I write this a little bit better? Could I change it in some way that would simplify it? Whatever it might be. But this now allows us to get 4/3, 3/3, plus essentially all of that squared. And that fella is the general solution to our differential equation. Okay, will you all say hi so that I can take attendance?
You mean particular solution, right?
I do indeed. Did you all get that deliberate mistake? Oh, God. How many times have I tried that excuse? Yeah, too many. You're right.
If I make a deliberate mistake on a test, do I still get points?
You will not do that in a test because you've seen me do it so wrong, you'll know the right answer. Nobody should do that mistake. That's just a careless thing. In fact, I don't think WebAssign even asks you to call it particular solutions, don't they? Just want you to stick whatever that is in a box. So you, but it's good to know what they are called. Okay. I got 2 more questions. Should be able to get them done. They are going to be in the same vein that we've been doing things, but each one's got something new in it. So this one is like question 12 in the homework.
Didn't you do 12 yesterday?
Did we? Cool.
Yeah, I think so.
That's off my list. Then we can do 9. Now, question 9 has a lot of writing to it, which I'm going to go and find out what the heck it says, so that I don't. Okay, so it says find an equation of a curve that passes through the point 0, 6, and whose slope at a general point xy is x over y. Wow. It doesn't look like the typical differential equation, right? I don't see any dy by dx's. I don't see, you know, any function like x squared y or x over y. Well, I see an x over y, I guess. But it is there. We just have to figure out how we're going to interpret what's going on. There's the first clue.
Isn't
When-
the derivative the slope of the slope of the curve at a point?
So the slope is x over y. So that last piece basically had hidden inside it the differential equation. The slope, right? We agree the slope on a curve is its derivative, dy by dx. And in this case, it's equal to that guy. And this little fella up here isn't just a side piece of information that we don't need. That guy is actually going to tell me something. Isn't that guy telling me y of 0 is 6? In other words, when x is 0, y is 6. So that is actually our hidden boundary condition. So although it started life off as basically a whole load of English, mathematically, isn't that the essence of what that is saying? Now, this is such a nice, no-frills differential equation. I'm going to let you do it, and I'm going to sit back and enjoy a drink. So, no pressure. You've got 2 minutes to solve that differential equation. No pressure, 30 seconds. Okay, let's get started then. Differential equation. Is it the right way around? Do I need to fix anything, or is it good to go?
Good.
It's good.
Good. So, crossover trick technique. So, power rule. Power rule. I think I could go through this pretty quickly. Shouldn't we double everything in sight? Which actually works out quite nice. And then take a square root. And we now have our general solution. This brings back a question, I think it was Christopher that said it. It went something like, do we always pick plus if this is plus? This is a situation where that's true. Would you agree that the y value is positive 6? And if the y value is positive 6, can't that only come out of a positive square root? So that does mean that we choose the pos version here. So it's going to be y equals that guy. And we're going to plug x is 0 and y is 6. So 6 goes here. And 0 squared plus c gets you c. And then you just basically got 36. Great. And you put that package together. And we have solved the particular solution. try something a little bit sneaky. Mostly the same story, but I'm going to have it pass through the point 1, 1, and we're going to switch the slope. So can you imagine I said basically, find the equation of a curve that passes through the point 1, 1, and whose slope at any given point x, y is y over x. Now, you might think that's not going to make a lot of difference. But it actually does make quite a big difference. For instance, you might think that the answer is just going to be 1 over this guy, right? Reciprocals. It's not. In fact, is this fraction the right way around? Do we have the right guy in the top and the right guys on the bottom? Oh, you're right, we got it. So they're going to have to switch places, aren't they? Now that y in the bottom could be written as y to the negative 1, and when I bring the x to the numerator, it's going to be x to the negative 1, which is correct, but not a good idea. Why am I calling it 1 over x instead of x to the negative 1, which is the same thing algebraically, but why am I writing it like this?
Easier to
Because
integrate.
once you cross multiply, you're gonna have like 1 over x dx, 1 over, and what equals 1 over y times dy, and then when you take the integral of both sides, that's an integral we know.
Right,
That
agreed. It's going to be a log of some kind. If you left it as y to the negative 1, might you try and use the power rule because it looks like it should be a power rule, and you'll get, well, you'd get y to the 0 divided by 0, which is probably not going to end well. And so we'll do the crossover. I wouldn't really want to call it cross multiply, although I know what you mean. We'll do the crossover. There we go. And this fella, just like you said, natural log of y. This fella is a natural log of x plus c.
You know, and if you raise everything to the e, you end up with the same answer that you would have if you just integrated with the power rule.
If you try
Because
to
I'm looking
integrate,
at y equals x plus c, which is eventually what you're going to get.
you've jumped ahead to the end. I hear you. Well, let's kind of make sure that I'm not hearing what I think I'm hearing. You're saying like that is okay. Well, if I do this, if I try to do this as a power rule, you add 1 to the power and then you divide by the new power. Do you see why that is not a good idea?
Yes, you.
Right? And why we went that route instead. Right? That might not be what you're saying, but I think I know what you're talking about later. This thing here is going to eventually be turned into a y equals. I wouldn't think it's too bad to turn into a y equals. Wouldn't we just raise h to the power of e, I guess? That's what I think I hear. Right, if you do e to the power of this guy, it's e to the power of all of that. Well, e to the natural log of y gets you y. E to the natural log of, well, let's just call it, for the time being, let's just call it that, right? Okay. Now, since I'm only going to be interested in the particular solution, even although that's not perfect, I could make it even prettier. I'm going to live with it because that's going to get fixed in a minute. Because x is 1, y is 1. Well, that's 1. And this guy is the natural log of 1, I'd see. Now, what number is the natural log of 1?
It's 0.
So won't that be 0 plus c, so c? Now, a couple of ways of doing this. Couldn't you just say, I know c is 0? Because e to the 0 is 1. If you really wanted to, couldn't you take the natural log of both sides? But whatever way you see it, do you agree that in this question, c is 0? Which means that y equals e to the natural log of x plus 0 just becomes that. And wait a minute, what's e to the natural log of x?
X.
X. Is that what you were talking about earlier, Christopher?
Yep.
Yeah. Do you notice that the difference between version 1 of our story and version 2 of our story, how much just changing where you put a variable can alter the solution an awful lot? I mean, that is a very simple solution. Basically, it's saying it's the only way that that's going to happen, right? The only way you're going to get this derivative always to be the y over the x and passing through that one point is if you had the equation y equals x, right? That's the only function in the world that has this unique property, that its derivative at any given point is its y coordinate divided by its x coordinate, and that y1 equals x1. Now, if you think about it, isn't the derivative of this guy 1? And in the line y equals x, won't the y and x be the same number? So won't that be 1? It matches exactly. Now, if I change this to 2, 1, wouldn't that give me a different value for c? And I would end up with some other straight line, I suspect, but not y equals x. I might end up with y equals 2x or a half x or something like that. And that is a nice point for us to finish, as far as that's concerned. Now, to worry everybody, we have one section to go. We're going to solve differential equations that are linear, right? So linear differential equations. And that's going to take place Wednesday and Thursday. Friday's a review day, Monday's our test. Now, as far as the final goes, anybody who has a problem with the timing of it, because it interferes with other class, right? And you don't want that to happen. Your final is designed for 2 hours, but if you're given 3, as a buffer in case you have an issue, send me an email and we'll do the usual of fixing a different time for you to do the final, okay? So if your physics final is like, interfering with my final because there's an extra hour and it's into their hour, then we can shift it, probably just shift it backwards or something. Any other questions?
What day is the
time
final?
and day is the
Okay, I got that in stereo, and I should be so prepared, I would tell you, but since I don't, I am going to do what everybody should do in my same situation. What do you think I am doing right now?
Check your syllabus.
I'm about to check my syllabus. Now, if you can wait, hang in there for a few seconds while I get this thing set up, we will have a look at our class. There we go. And I'll switch it over so you can all see it. Boom. Basic. And darn it if I can see it. I believe it's here. No, it's not. I'm going to do it this way. I know you can't see it yet, but you'll see it in a second. There it is. So I should be able to make that a little bit bigger because I can't see too clearly on this screen. There we go. Syllabus. I wonder if it's under course assignments as well. I should have put it two places. There you go. Thursday the 10th. 10 till 1. It covers all the chapters. Right. Most of you probably will only need 10 to 12 because it's, WebAssign tells me how long questions last and I always make it 2 hours. But just in case you need extra time. I think I did, but I may not have. Did I mention the fact that only the top 4 tests count? Right, so I won't go over that again. If there are no more questions, I think we are going to call it a day. So bye-bye, everybody. Oh, wait a minute. Do you want a joke?
Yeah.